Hi friends, welcome to follow up. Let's continue our explanation on search range shrinkage strategy. So this problem can be regarded as a follow-up for LeetCode problem 162. Here we are talking about problem 852, peak index in a mountain array, right? So our plan will be the following. First, we are going to digest the requirements of the problem, and then we do the coding, and in between we are going to explain the thought process and the major idea. So this problem actually is related to binary search. So we have a playlist on binary search. I hope that you can check out that if you find it's a little bit difficult in understanding the content here. With that said, let's look at the problem requirements. So here, an array is a mountain array if the following property holds. First, the length is greater than or equal to 3, right? And then there are some index in between. It's not the leftmost, also not the rightmost, but it's a middle one, such that up to this index, the array keep strictly increasing. And then after this one, and include this index, it's going to be strictly decreasing, right? So given such a mountain array, we want to find the index, that is a peak, right? So here the major requirement is that we must solve it in a logarithm time complexity. So this requirement actually is very suggestive, right? So basically we can think of something related to binary search. So here we have 3 examples. If you look at the first one, obviously the index 1 is the peak. And if you look at the second one, the index 1 corresponding to the peak. And similarly for example 3, index 1. So here the length is bounded below by 3, greater than or equal, and bounded above by 10 to the power 5, right? Then the element is non-negative and bounded above by 10 to the power 6. So this array is guaranteed to be a mountain array. In other words, we have a valid result anyhow. So with that said, we are ready to look at the coding. So here I would not explain on the general usage and the usage pattern of binary search. So if you are interested, you can check out our binary search playlist. So here we focus on one part, that is search range shrinkage. So first, let's look at the major condition. So what we want to do is to find the index I such that AI is strictly greater than AI plus 1. So that's it, right? So the reason is that if we are in the left of I, including I, so the array is strictly increasing. And afterwards, if we are to the right, that is from index I onwards, the array will be strictly decreasing, right? So we want to find the very changing point. So here, I'm going to explain the mainly the search range shrinkage part, right? So I'm going to write search range shrinkage. But in general, some people also call it the binary search. So first, I'm going to get the length of this array, and then we can say the search range will be index 0 and n-1. Notice that the result will not be 0 or n-1 due to the assumption, right? It's a middle one. And then we can do the while loop. So while low is less than high. So we're going to say mid. The mid, we can do shrinkage like this. So each time we shrink 1/2, right? And then we want to check condition. We want to check this condition or its complement first. So if say A mid is less than A mid plus 1. So mid is for sure less than mid plus 1. This condition basically says if the index is larger, the value will be larger, which says that we are still in the increasing part, right? Then we can set low to be made plus 1. Then this will ensure that including low and onwards, that will be the range for our search for the peak. So otherwise, so because the elements are different, then we are going to have a made is greater than a made plus 1, which says that if the index is smaller and the value will be larger, so this means that we are in the range of a decreasing range. Then we are going to set high. So here, let's see, I will use low, and high will be made, right? So here I use made because we want to see from the beginning up to and including this made. So we know there must be a peak, right? Because the peak is in the changing point part. So then we just need to do the correct return. So we're going to return low. The reason we return low is that it's always in between. It's make this condition true, right? So now let's look at the test. Yeah, it passes one example. Now let's look at the generic case. Yeah, it passes all the cases. So here I would like to point to one condition. That is, this array is guaranteed to be a mountain array. So in other words, there must be some return. So actually for this problem, you can also return high, right? You can do a test. And if you like, maybe you can also return mid. Mid is not right. The reason is local, right? So let's see, high. In general, I would prefer to return low. Actually, the return sometimes can be crucial, right? In general binary search. Here, let me state a little bit more. So in general binary search, so basically, if we're not like we find a element in a sorted array, that's a vanilla usage. In general, we need to define the binary function to produce monotonicity or order. So in that case, depending on how you do the shrinkage, so here I increment from low then up to 1/2. Some people also do high minus the 1/2. Then depends on the direction, you can accordingly return low or high. But for some problems, low and high will be the same afterwards. So this is the point to notice. Actually, another point to notice is how you write this condition in the while loop. Sometimes less than or equal, and sometimes strictly less or change direction greater than or equal. This is also important to notice. But actually those intuitions can be gained by some practice. So therefore, I will suggest you to check out our binary search playlist to see more use cases, and especially you can think of the returns in those examples. So with that said, I guess that's about it for this specific problem. Thanks.